Next topic, we're going to give an overview of Java atomic operations variables. And this will give you an understanding of the programming language features that support these concepts that we just talked about with respect to atomicity, visibility, and ordering, as well as the class library features that support these things as well. And they occur at several different levels. So there's several types of atomicity in Java. The first type, which is the simplest type, but also the most efficient type, are so-called volatile variables. And anybody here who's ever programmed in C or C++ has probably heard the term volatile if you've gotten any kind of experience. That is not at all what we're talking about. If you know C and C++, volatile, erase that knowledge from your brain at the moment when we're talking about Java, because they have nothing whatsoever in common. So what are volatile variables? They ensure a variable is read from and written to main memory by threads running in processor cores, and do not stop in and do not go into the cache. They are read directly to and from the memory. They do not get stuck in caches. The cache could be updated, of course, but that's just a byproduct of writing to main memory. So they go right to main memory. Let's take a look at an example to illustrate this. And it's a very simple example. It's a very interesting example that involves sharing a field, which in this case is called val, an int, between two threads. And this particular program, believe it or not, will alternate printing ping and pong between threads T1 and threads T2. And if you want to convince yourself of this, you can go take a look at this program, which implements this, and you can run it and see that it actually does what I'm telling you it's going to do. So here's how it works. We make the int field a volatile. If we do not make the int field a volatile, and you can do this if you run the program I showed you, if you go run this thing, this program won't work correctly. So this program depends on volatile being in use. So volatile means a read or a write to the variable goes directly to memory, which makes it instantly available to other threads, or effectively instantly available to other threads. In this case, we have two threads, T1 and T2. So basically, by defining val as volatile, reads and writes bypass the local caches. So as you can see here, what this thread does, this particular thread is inside the play ping pong method. And this first thread here, let's call that thread T2, that's the listener thread. And then that is going to be reading from val atomically. So we have a loop where we read the value of val, and then we loop through this, and then we read the value of val and assign it to the loop variable, LV. So just keep that in mind. Those are atomic reads. Here's thread T1. This is the changer thread. So this is the listener thread or the reader thread. This is the changer thread or the writer thread. And this will write the value LV, which is the loop counter, to the value of val. And so what happens here is it starts out at 0, and this thing goes from LV equal val. So we start out with the value of 0, and we're going to go up till max, whatever max is. It could be 4 or 5, whatever, however many iterations of ping pong we want to do. And so if LV doesn't equal val, then we go ahead and print pong. And then we set LV to val. And so that thread starts up, and that's the loop that it's going to do. Down here, this guy starts up, and he starts up by writing ping, and then he increments the loop counter by 1. That's also an atomic read, of course, here to assign that. And this thing will then set the value to val. So notice what happens when this thing first starts up. LV and val are the same. They're both 0. So this loop will not actually print anything. So pong won't start first. Down here, when it starts up, we print ping, and then we assign the loop value to val. So this starts out at 0, loop value goes to val. Oh, I'm sorry. Loop value starts to there. And notice how we increment the loop value by 1. So it'll now be 1. And so we update val with the loop value, which is now 1, and this guy goes to sleep. Now that this thing is changed from 0 to 1, the next time through this loop, LV won't be equal to val. So in that case, it goes ahead and prints pong. And then it assigns LV to val. So the way this works, if you run this thing, it'll go ping, pong, ping, pong, ping, pong. But if you take out the volatile, it won't work because the reads and writes are not atomic anymore. There's also a whole slew of low-level atomic operations that are defined in Java's unsafe class. And we'll talk more about these things. They're very low level. This class, this unsafe class, is designed for use by the Java class library implementers, not by mere mortals like you and me. So these are cool things to know about, but you actually can't access them. In particular, the compare and swap methods in the unsafe class do some really cool things. We will talk a lot about that later. I'll explain how they're implemented. Don't worry about the details now. Basically, what this does is it allows us to atomically compare the contents of memory with a given value and modify those contents to a new given value, if and only if they're the same. We'll come about and talk about that later. Compare and swap methods can be used to implement so-called lock-free algorithms, which is a very funny name because it doesn't mean that this thing doesn't have synchronization. It just means that there's no locks that are sleeping. It's basically spinning. And you will do something like that for your assignment 1B. And again, we'll talk more about how compare and swap operations can be used to implement a simple mutex spin lock. And that's what you'll be doing in assignment 1B, although your solution will not look quite like this because this is kind of in pseudo C, C++ Java code. Synchronizers in the Java class library use these compare and swap methods extensively. With Java 9, which we now have access to mercifully because Android now supports Java 11, so of course it has Java 9, there's a new class, new to Java 9 and beyond, called a Var Handle. And this allows mere mortals like you and me to do these low-level compare and swap operations without having to rely on the unsafe class, which we don't get access to as mere mortals. So this exposes the concepts that unsafe had up to programmers like us. And these operations that you can do with var handles, which I'm not going to talk about in great detail here because it's very cool but a little complicated, they are primarily used for atomic or ordered operations, like compare and swap operations to implement atomic fields. And I'll explain that in more detail when we get to that point. So again, just to reiterate, the var handle class was designed to be used by apps, like the things we write, unlike the Java unsafe class, which was only intended for class library writers. And they've actually gone back and retrofit a lot of the atomic classes in modern Java to use var handles instead of the unsafe class, so you can actually see how they work. So the things we've talked about so far are really, really, really low level. We'll get some experience with that, but we're going to do it through slightly higher level wrappers called atomic classes. And here's a smattering of atomic classes: atomic Boolean, atomic integer, atomic long, atomic reference, and you get the chance to play around with some of those things for the next assignment, assignment 1B. You can use these particular classes, which internally use either unsafe or var handle classes, to implement lock-free methods. And so the methods in all these classes are lock-free. They don't block, they spin. And in particular, atomic long and atomic Boolean are some things we're going to talk about because you're going to have to learn how to use some of those things for your programming assignment. So that's the end of the overview of Java atomic operations and variables. In the rest of the time, we're going to go into examples of these things in more detail so you'll be prepared for assignment 1